Hello everyone, and welcome to lesson 1.3, Vectors and Scalars. The first slide that I always like to start off with is this one right here. Okay, so the reason why I like to start with this slide is because it always has something called the data booklet reference, and it's always going to be in red. So this slide will always tell you which formulas you should expect to see in this section. So in 1.3, we should expect to see a formula for a sub h and a sub v, as well as that diagram. So let me go to the formula booklet right now. And this is what I was saying in the last video. Make sure that for every lesson you have your formula booklet in front of you, your data booklet. And so since this is section 1.3, I'm going to turn the page until I get to the equations core. Okay. So like I mentioned last time, you've got 1.2 here. Here's box 1.3. We skipped 1.2 because this was IB. So box 1.3, vectors and scalars. So that's our section today. Here's the diagram and here are the formulas on the slide. All right. So make sure that you're always in, excuse me, you're always in tune with that and you know what to look for. Okay, let's get started. All right. This other stuff, this is for the IB, so you don't need to go and read it. All right. So the first things we're going to look at here are what is a vector quantity and what's a scalar quantity. These may be terms that you have heard of before, and if not, that's completely fine. A vector is something that has magnitude and direction, but a scalar quantity only has magnitude. Okay, so what's the difference? Well, think of it like this. Let's go to the page for a second. Vector. Okay, so this thing has magnitude plus direction, and a scalar is a quantity that just has magnitude. Now, there are some quantities that you can simply just stick a direction on the end of and turn it into a vector. So, for example, if I say that Susan has driven 500 meters, well, then I can just add a direction onto that and say that Susan has driven 500 meters west. Notice that I'm putting the direction in square brackets. That's generally the way it's done. Okay. So scalar, vector. But notice that between these two, all I had to do was stick the direction on the end of it. Not all quantities that are scalars can have a direction just stuck on the end and have them become a vector. Okay, so for example, if I say that Matt tells me that the temperature outside today is going to reach a high of 33 degrees Celsius with the humidity, I can't go ahead and then say, Matt says the temperature is going to reach 33 degrees Celsius north. That doesn't make sense. The temperature doesn't have a direction. Okay, so temperature is an example of a scalar quantity. Now, I can actually differentiate between these two as well. If I just say someone has traveled 500 meters, this is a distance. Now, 500 meters west, this is a displacement. And this is where things start to get a little confusing. Okay, displacement is not just a distance with a direction associated with it. Distance is the total length that you have traveled. So for instance, let me just do something over here. For instance, if I go, okay, so I said west first, right? Okay, so let's say I go 500 meters west, and then I go 100 meters north. Okay, so the total distance that I've traveled now is 600 meters. Yeah, 600 meters, okay, in this case. But the displacement is, well, what's the difference in distance between where you started and where you finished? So if I wanted to get to where I started to where I finished faster, what would this distance be? And that's my displacement. So that's displacement, and then the distance, 600 meters. So notice here, the displacement would not be 600 meters with the direction associated with it. You can see this is a right angle triangle. Okay, so how would you find the length of that side? You would use Pythagorean Theorem, right? And Pythagorean Theorem, well, we know that the hypotenuse is the longest side of a right angle triangle. So that displacement is going to be larger than 500, which is already the biggest side between the two adjacent sides. But it's certainly not going to be exactly 600. I doubt it. Well, actually, we can determine it right now. Let's grab our calculator. The displacement is going to be the square root of 500 squared plus, well, let's actually do this whole thing in brackets, 500 squared plus 100 squared. Okay, so that's 509.9, so approximately 510 meters. Now, as for the direction, and I know I'm actually getting quite a bit ahead here, but I just wanted to make sure you understood this difference, but we'll come back to this. For the direction, I mean, clearly this is not just, this is not north, this is not west, this is some kind of northwest direction. Now, I can't say that it's 510 meters northwest. If I say exactly northwest or northeast or southeast or southwest, that automatically implies that this angle is 45 degrees, but we don't know that it is. So what physicists do is they label this angle, and we use the Greek letter theta. Okay, so the Greek letter theta, we can determine this angle, and in grade 10 you learned how to do that. It's a right angle triangle, and I know the opposite and the adjacent sides, so that means I can use tangent to solve. Now again, I'm getting way ahead here. I'm going to get way more into this towards the end of the lesson, but I just wanted to make sure you understood that there is a distinction there. Displacement is not just necessarily a distance with a direction tacked on the end. Although, if the person just travels 500 meters, like just this piece, then yes, in that case, the magnitudes are the same. Okay, let's go into some other examples of scalars versus vectors. Another example of a scalar would be mass. Okay, I can say that the mass of the child on the ride is 30 kilograms. And I can't say that the mass of the child is 30 kilograms north. It doesn't make sense. Okay. Examples of vectors. As we're going to see, forces are vectors, and forces are measured in newtons. What else? We've got velocity, and then the I guess symmetrical counterpart here for scalar would be speed. The difference between speed and velocity is like the difference between distance and displacement. Sometimes the number can be the same between these two. After all, they're both measured in meters per second. The magnitude of these two can be the same, but not necessarily. Another vector would be acceleration. There are so many vectors we're going to learn about this year, and it'll just come up as we get to it. And so hopefully that's okay. I'm just going to mention one more thing. For distance and displacement, generally speaking, for scalars, we use this kind of notation. So for distance, usually we use the letter S. I know it's a little bit strange. Most of you are wondering why not D. Actually, in higher level physics and even in mathematics courses in high school, especially the grade 12 maths, you're going to see that distance is always represented by S. Now, if distance is S, displacement usually, now in books, what they would do is they would just bold the S to indicate that it's a vector. Another way to do it is just to put a regular S with the vector symbol on top. Either one of those would work. Some people put a half arrow. I like to put the half arrow. Some people like to put the full arrow. That's up to you. But for our purposes, just putting a regular S will also mean displacement. Okay, so I just want you to understand that. So there's 4 ways of putting vectors, and there's 1 way of putting a scalar. All right, we're going to get into all of this slowly as we get through the lesson. So I just want to go back to the slides and go to it when we get to it. All right, example, a force is a push or a pull and is measured in newtons. Explain why it is a vector. Right, so if you are pushing a heavy table across your kitchen floor, all right, so that's a push, right? So you have to apply some force. So your muscles through your hands are applying a force onto the table. You're moving it across the floor, but you're pushing it in a certain direction. Okay, so when you guys would, let's say if you are pulling some children on a sled and you have a rope attached to the sled, if you're pulling it towards you, or you're playing tug of war and you're trying to pull the rope towards you, that's a pull, but you're pulling it in a certain direction. So the direction is significant there. So force is a vector. Okay. So if you need to, you can pause the video here and you can copy down what's on the slides. But we have to indicate 2 things, right? So if a force is a vector, that means it has a magnitude and it has a direction. So far, even on the page that I've been writing on, I've been indicating directions as things like north, east, south, west, angles. I mean, it could be left, right, up, down, some kind of direction giving system that makes sense. We can even say things like 20 degrees counterclockwise from the positive x-axis. Okay, that can also be a way of describing direction accurately. Okay. All right. Explain why time is a scalar. So that's another good one. Right, so on our sheet, we indicated two nice examples of scalars, which are temperature and mass, but time is also one. Right, so if 5 minutes passes, you can say that 5 minutes have passed. You can't say that 5 minutes east have passed. It doesn't make sense. Right, so time has to be a scalar quantity. No spatial direction involved there. Again, if you need to, pause the video here and copy down the notes. All right, give examples of scalars in physics. All right, so we actually did that just now on our slide. Speed, distance, time, and mass. Okay, we also saw temperature. Even though I gave it in degrees Celsius, whether it's in Celsius, Fahrenheit, or Kelvin, which is the accepted SI unit for temperature, they are all scalars. Vectors, we also gave a bunch of examples of those, and these were them. Velocity, displacement, force, weight, acceleration. Now, weight, we didn't write, but weight we were introduced to last time. In fact, it's a little bit redundant that it's there in the first place because weight is a type of force, if you recall. Weight means force of gravity, right? So, and remember, when you stand on a scale, it's not measuring your weight, it's measuring your normal force, right? So those are sometimes the same number, but usually they're different. Okay, vector and scalar quantities. So speed and velocity we're familiar with. All right, so in the car, on the dash, you've got the speedometer, right? The needle tells you how fast you're going. As the needle moves, you know that you are also accelerating since your speed's changing. But let's say that your speed's constant. Some cars will also have a compass integrated into it. It'll tell you what direction you're going. So if you have your speed and a direction, well, we can call that velocity. And if you just have the speed, then that's just the speed. But once again, I have to really strongly emphasize that velocity is not just speed with a direction. Okay, so yes, it is represented by that here. And this is correct still, but velocity can be very different. Just as displacement and distance can have the same magnitude, it is usually not the case. Speed and velocity may have the same magnitude, but again, it is usually not the case. We'll learn more about how to calculate velocity, displacement. Well, today we're going to learn about displacement, but velocity you'll learn more about later on. Okay, suppose the following movement of a ball takes place in 5 seconds. All right, so we can see how much time it took. You could measure the distance, how many ticks it crossed. Okay, so for the time it took to travel 15 meters, we can say that 15 meters in 5 seconds, that's a velocity of 3 meters per second. Notice that there's a little plus sign in the front. That's simply to indicate that the ball is moving to the right or in the positive x direction. Okay, now if you have this green ball, it's going to move to the left. It's moving over the course of 4 seconds, 20 meters. But since it's moving left, it's moving the opposite direction of the red ball, right? So we have to indicate that since it's in the opposite direction of the plus, we have to put the minus sign in front, okay? So 20 meters over 4 seconds is minus 5 meters per second. Now, where does the minus come from? Not just the fact that it's going left, but this is the idea. While the distance in this case is 20 meters, the displacement is 20 meters left. And since left is going in the negative x direction, we put the minus sign in front of the displacement. Whereas up here in the first case, we had the ball traveling to the right. So we put a positive sign in front of the displacement, right? Displacement over time is velocity. In this case, because the ball is just traveling along a straight line, the displacement and the displacement and the distance and the velocity and the speed will have the same magnitudes respectively. Okay. Now we can represent vectors as arrows. That is extremely important. Not only do we symbolize vectors, let me go back to the page here for a second. Not only do we symbolize vectors with the arrows on top, again, you can symbolize it with the arrows, bold it, or just leave it as is. we symbolize vectors with arrows. So here in this case, you see I've drawn the arrows in this picture. This is demonstrating individual vector movements. So first this person starts, they move 500 meters west, then they displace themselves 100 meters north, and this is their overall displacement. Right? And the length of those vectors indicates the magnitude of that vector. That's important. So the length of the vector indicates its magnitude. Okay, so how do you know the direction? Well, you just look where it's pointing, right? So this arrow is pointing left. So if I had a compass here, this would be north, right? East is on the right, south, west. That's how I determine it. Let's go back to the video. Now, we don't need those little tick marks. We don't need those scales. And in fact, these 3 meters per second, 4 meters per second, they don't have to be necessarily left and right. In the case of the example we just saw on the previous slide, they do because the object was traveling along the positive x-axis, hence the +3, and along the negative x-axis, well, or in the negative direction, hence the -4. Vectors don't have to just move along the positive or negative x-axes. They can move in any direction, right? There are 360 degrees worth of directions just in a two-dimensional plane, right? So there are infinitely many directions that the vectors could point. So if your vectors are pointing in different directions, not just left and right, it no longer makes sense to put the plus and minus signs in front of them anymore, okay? So plus and minus is just for linear, one-dimensional motion. As soon as you get into two-dimensional or higher, don't put the plus and minus in front of anymore, because it doesn't have any meaning. All right, practice. Which of the following contains 3 scalar quantities? Please pause the video, attempt this for yourself, and then unpause it, and we will talk about the solution. Okay, hopefully you had a chance to pause the video, think about it. If you haven't, do it now. So looking through the options, all 3 of them have to be scalar quantities. Now, charge, you may or may not remember from grade 9 science what that is. Density, you might have an idea. Speed, well, we just talked about speed. Speed was a scalar. We have mass. Mass is a scalar. So we're looking at charge and weight. Now, this question's quite interesting. It actually goes against the norm. You see how weight actually appears on 3 out of the 4 choices and it doesn't appear in the first choice? Usually when that happens, generally one of those answers is correct. But not in this case, because if you recall, weight means force of gravity, right? Force of gravity is a force. It's in the name. It's a vector. So it has, by definition, a direction, right? So it's not a scalar. So that means this B is not satisfying the requirements. C nor D are satisfying the requirements. The solution must be A. All right. So therefore, A is the correct answer. All right, combination and resolution of vectors. So we have 2 vectors here, A and B, and they are drawn to scale, which means you could take a ruler up to the screen, measure the length of A and B, and that would actually be the magnitude of the vectors. Okay. So this is what I was mentioning earlier. In print, usually they bold the vectors. In the textbook, you'll probably see it like that. And every book is a little different. I'll mention that too. Some books bold it, some books put the full arrow, some books put the half arrow. Some books don't even put the arrow. So this is what I mean. I want you to get used to all different versions. If you're asked to solve for a scalar, make sure you don't bold it or put any arrows. If you're asked for a vector, you can go with any one of these representations, or you can simply follow the way I'm going to solve it in the problems, as you'll see throughout the videos. All right, now getting used to describing these arrows. Each vector has a tip and a tail, so you have to get used to which is which. The tip is the pointy part, and the tail is the end. Right? It's as simple as that. So I'm going to be using this terminology more and more. So for example, let's say you want to get the sum of vectors A and B. All right, so kind of like how we looked at before. Well, we had a displacement 500 meters west, 100 meters north. Adding vectors is a little different than simply just adding the magnitudes. If we want to find the sum of vectors A to B, we use a process called adding the vectors tip to tail. Okay, so what you do is essentially you take one of the vectors, so let's say you take B, you take the tail of B and you move it so it's attached to the tip of A, keeping in mind that the length of this arrow and the direction that it's pointing has to be the same, so down and slightly to the right. Okay, so this gets translated over until it attaches like this. Now, you could just as equally move A and attach the tail of A onto the tip of B. There's no problem there. You're going to get the same result. And in fact, if you'd like, you can try it after this. You'll see that you'll get the same answer. And the reason why you can do A to A plus B or B plus A is because addition is commutative. And you've known that since you learned about addition. Okay, now the sum. Adding the two vectors, remember you have a start and you have a finish point. The sum is simply where you originally started to where you finished. So the tail of the first vector to the tip of the final vector. That is the sum. And again, we saw that with the displacement on the sheet of paper. Now, how do we find that length? Well, there's a couple of options. Now, let me just go back to the paper for a second. If it's a case like this, I have a right angle triangle, and I know that because I'm going west and north. The compass directions are all 90 degrees to one another. So I know that that's 90 degrees. I have a right triangle. I can use Pythagorean Theorem to find the length, and I can use SOHCAHTOA, usually it's tan of theta, to find the angle. Now, that's because it's a right triangle, but even if it's not a big deal. In this case, I don't have a right triangle. It definitely doesn't look like one. And even if it does look like one, you cannot assume that it is unless you know for sure. For example, if you have the compass directions. So you can solve this, for example, using a combination of sine law and cosine law. We'll do examples of those too. Okay, so there's the sum. All right, so this is a more entertaining version of the previous example, but same thing. Okay, so you've got a pirate saying first we're going to pace off the first vector A, then we're going to pace off the second vector B, and then we're going to find the treasure. Okay, right. So here we go. We've got a treasure map, and we are trying to get the treasure. So here we're going to start on the bottom left. We're going to take a certain number of paces off in the direction of A. We're going to take a certain number of paces off in the direction of B and arrive at the treasure. Now, this pirate has a couple ways of traveling. Either he can travel along A and then travel along B, or he can simply go the shortest distance, which is the sum of vectors A to B. Right? So most likely he would take the shortest distance to get there fastest. Okay. Here we go, another practice problem. This one really requires you to imagine these vectors in your mind. Two forces of magnitude 7 newtons and 5 newtons act at a point. Which one of the following is not a possible value for the magnitude of the resultant force? I'm going to switch screens here for a second, okay? But I want you to really pay attention to those numbers. So we're looking at the sum of the two vectors, 7 and 5 newtons, and we want to know which one is not possible to be a sum of the two. Okay. Okay, so we have 7 newtons and we have 5 newtons. Now the options are 1 newton, 3 newtons, 5 newtons, and 7 newtons. All right, so remember when you add vectors, so let me just do that here quickly. If you have two vectors, A and B, you add them tip to tail. All right, so actually I don't even have to label it like that. So I would take the tail of B and attach it to the tip of A. All right, so here's A and here's B. And the sum goes from the tail of A to the tip of B. Now, what I like to do is always draw the sum as a dashed line, just so it looks visually different. So this is A plus B. But you still got that arrow because it's a vector nonetheless. All right. Now, this was able to be done because I already knew the direction of A and B. Now, I know the magnitudes as well here in this case, but I don't know the direction. So I got to figure out, well, how can two vectors of 7 newtons and 5 newtons be added such that I get the biggest value? And you know how to add the vectors, tip to tail. Well, how can you get the biggest sum with vectors A and B? What directions would they have to be going in? Think about that. Well, if you want the biggest sum, since you go from the tail of A to the tip of B, they would have to be back to back, right? So let's say you had the 7 Newton force and you had the 5 Newton force. When you add them, if they're going in the same direction, remember the sum is from the tail of the first vector to the tip of the final vector. Now this sum I'm going to have to draw underneath, otherwise you're not going to see it. this would be the sum. This would be the 7 plus 5 newtons, right? Because they're exactly back to back. So that's going to be 12 newtons. So the maximum value is 12 newtons. Now looking at the options here, there's no answer above 12 newtons. So that's good. So they're still all in the game. Now, since we already inspected what the biggest value they could be when they're combined is, let's look at what the possible smallest value they could be is when they're combined. Well, the smallest value they could be is if they're going exactly in the opposite direction. So if I have 7 newtons, let's say, going in one direction, and the 5 newtons going in the exact opposite direction, right? So remember, the resultant goes from the tail of the first vector to the tip of the final vector. So it looks like this. There's the resultant, that little arrow right there. And how long is it? Well, if that's 7 and that's 5, that's got to be 2, right? So we have at biggest 12 newtons, at the smallest 2 newtons. That means every other option has to be somewhere in between this long arrow and this short one. And just for the sake of argument, imagine instead of just going linear to each other, you had the 7 newtons in this direction and you had the 5 newtons in this direction. Let's say 5 newtons like this. What would the sum look like? Well, it would look something like this. But that line is not going to be 12 newtons, not at all. All right. You don't even need to have the angles here to work out cosine law and sine law to figure that out, because the biggest arrow would have to be if this arrow was completely flat. Okay. Take another example. Let's say they were at 90 degrees to one another. 5 newtons, 7 newtons. There's the sum. Again, bigger than 2, smaller than 12, right? Let's do one more example. So if you have 7 newtons and let's say your 5 newtons are going like this, well, once again, that arrow is smaller than 12, but bigger than 2, right? So that means you have to look at the extremes. Smallest, and this is the largest. And again, we didn't see any value here larger than 12, but I can see that there's a value smaller than 2, and that's 1 Newton. So therefore, 1 Newton is not a possible value for the magnitude of the resultant. Now, I do want to indicate one thing. That is a new piece of terminology in this question, resultant. So the resultant is another name for the sum. Okay? So when you add vectors together and you get the result, it's called the resultant. That's the name of the vector. All right, so going back, and of course the same solution that I just discussed is here on the slides. Now there's a nice animated version of it here. So you've got the red arrow, which is the 7 newtons, and the blue arrows are the 5 Newton forces. You can see that when they're exactly oppositely directed, you get the shortest pink arrow, the vector sum. And if you keep increasing the angle, that arrow becomes a little longer, and it's the longest when they're exactly back to back. Okay. Let's try this one. The diagram below shows 2 vectors, x and y. Which of the vectors below best represents the vector c that would satisfy the relation c is equal to x plus y? All right, so x plus y. I'm going to go to the page here. So I've got x and I've got y. And c is equal to x plus y. All right. So before you look at the answers, what I am a firm believer of, especially for multiple choice, believe it or not, is the hardest part of any exam. And if you haven't noticed that yet, that's just due to the type of questions you've been given. Moving into grades 11, 12, and even more significantly university, you're going to see multiple choice is the hardest because a lot of the answers might look the same. So my advice to you is figure out the answer before you look at the options. Right? Have a good idea. C is equal to x plus y. And again, that's if it's possible. So I'm going to draw x, okay, plus y. So I'm going to take this vector and translate it over here. Okay, so take the tail of y and attach it to the tip of x. All right, so it's going to look something like this. So the sum is going to be from the tail of the first vector to the tip of the final vector. So it's going to look like this. So that's c, which is x plus y. So I'm looking for a short arrow that's in the up towards left direction. A short arrow up and left. So that looks like B right here. All right, so that's the only possible answer. All right, there we go. So now we've seen how to add vectors. We're going to look at how to subtract vectors. I'm going to show you this on the sheet again because I think it's just easier this way. And you know what? I'm going to use x and y as an example for this. So c here, I had c is equal to x plus y. Imagine I had c is equal to x minus y. How would I figure that out? Well, remember that subtraction is just like addition, just like multiplication is just like division. You just have to multiply or divide by different numbers depending on which direction you happen to go. Okay, so let's say I wanted to do 4 minus 2. Okay, that's really simple to calculate, but I want you to see this in a slightly different way. Instead of seeing it as a difference, I want you to see it as a sum. 4 minus 2 is equivalent to, and in case you haven't seen this symbol before, when you have an equal sign with a third horizontal line, that means equivalent to. All right, so 4 minus 2 is equivalent to 4 plus negative 2. Same thing, right? And so the answer is just 2. Pretty easy. So what I'm going to do is the same for vectors. Instead of having c is equal to x minus y, I'm going to have c is equal to x plus negative y. All right, so this way I still am adding two vectors. In other words, I still add them tip to tail. But I have to figure out what negative y is. So let me just draw these here again. So I have x and I have y. Now, negative y. The magnitude of a vector is the absolute value of its size, right? So whatever length y has, putting a negative in front of that doesn't change the length. What it does is it changes the direction. Okay? Imagine I told you Susie is traveling 5 meters north. Okay, so you would be able to draw that. Oops, sorry. 5 meters north. So something like this. So there would be an arrow. It's 5 meters. Of course, there's some scale there, and it's going in the north direction. Now, what if I told you that Jane is traveling 3 meters in the negative west direction? What's negative west? Negative west is east. Okay, so that means she's traveling 3 meters east. Now, you can put the negative in front of the west, or you can put the negative in front of the 3, negative 3 meters west. They're both equal to 3 meters east. All right, so negative just means, where is it? Negative just means you're going in the opposite direction. So we actually have a special name for this. So negative y is the opposite vector of y. Now it's interesting because in physics you have to learn about vectors in order to solve essentially everything. And one of the major components, almost half the course of calculus and vectors in grade 12 is knowing what vectors are. And when we introduce vectors in that course, we start learning about this. Like, what is a vector? What's a scalar? What is an opposite vector? You guys are learning all of that now. And this is what I mean. It already is a no-brainer that if you're taking physics, you should be taking calculus because the two subjects, they go hand in hand. Just like if you're studying biology, you have to take chemistry. Those two go together. You got to take math with physics. It just is, that's the way it is. All right, both subjects have so many places where they cross over. All right, so let's draw the representation of negative y. So it's going to have the same magnitude, but it's going to go in the opposite direction. So there's negative y. So all that I'm doing now is I'm going to take x and add negative y to that. So remember, I'm going to add them tip to tail. So you can take negative y and stick x onto the end, or take x and add negative y onto the end. Okay, I'm going to take x and add negative y onto the end. It doesn't matter. So x, now take negative y and stick it here. X plus negative y. And the sum always goes from the tail of the first vector to the tip of the final vector. So this is x minus y, or x plus negative y. Okay? I just figured it would be easier for you to see it like that than see it in the slides. All right. So, and that's exactly what's being demonstrated here. Instead of a minus b, we have a plus negative b. So we reverse the direction. So there's b. Here's the opposite of b, which is negative b. Okay, so therefore, if you have a minus b, there's your a. Add to it negative b. And there's your sum. From the tail of the first vector to the tip of the final vector. That's your resultant. All right, here we go. So now that you saw what to do with x and y, here are slightly different x's and y's. The diagram below shows two vectors, x and y. Which of the following best represents the vector z, which is equal to x minus y? So give that a try, pause the video, and see if you can solve that. Okay, hopefully you had a chance to give that a try. Let's go to the page and work this out. All right, so we have x and we have y. Now this time they're drawn tip to tip. Now they can be drawn any way. It doesn't matter how they draw it, but you have to remember that when you attach them, they have to be tip to tail. But we're not adding x and y, we're adding x and negative y. So z is equal to x minus y, and that's equivalent to x plus negative y. So if I already have y here, remember negative y is the opposite vector. So it has the same magnitude, but it's in the opposite direction. So what I'm going to do is take x, right, and negative y and put them together. So take the tail of negative y and attach it to the tip of x. So that means I'm going to have something like this. X, and take this to the end here. There's negative y, and when you add the vectors together, from the tail of the first vector to the tip of the final vector. So there's x plus negative y, aka x minus y, which is equal to z. Okay, so we have a relatively long arrow, okay, longer than x or y originally was, and it's going downwards and to the right. Let's look at our options. Okay, so these two are shorter than x and y, these two are longer, so that's going to be one of the right ones. And this one down here is going down and to the right. So that's the correct answer, B. And there's the animation for it as well. Okay, so we saw how to add vectors. We saw how to subtract vectors. Now we're going to look at scalar multiples. And I keep telling you guys, this is really great because when you get to grade 12 calculus, you're already going to know what a resultant is, what an opposite vector is, and now what a scalar multiple is. Okay, so scalar multiples, let me actually just go to the page here. If you have a vector, let's call this, let's call it W. Okay, if I have the vector W, well, it looks like this. If I want to take a scalar multiple of it, so let's say I want 2W. That means it's in the same direction W was originally in, but it's twice as long. Okay, so something like this. So there's 2W. But that scalar multiple doesn't just have to be bigger than the original number. Even though there's no number written here, you know that technically there's a number 1. So this is 1 of itself. This is double of itself. I can even make it half of itself. So I can do 1/2, or let's make it 1/3. Okay, 1/3 W. So it's going to be 1/3 the original length. So it looks something like this. Now that scalar multiple can be larger than 1, it can be smaller than 1, it can even be negative, which would also fall under the umbrella of being smaller than 1. If I wanted to make it minus 1/4 W, it's a quarter of the length, so imagine cutting this in half and in half again, but it's in the negative direction, okay? Something like that. I can also have minus 1.5 W. Okay, so 50% longer than this in the opposite direction. Now, with scalar multiples, notice that I can only have it going in the same direction or the opposite direction. I can't change it to any of the other directions in the 360-degree plane, okay? Because all I can do is put a plus or minus in front. So just keep that in mind. But those are all scalar multiples. All right, so that's what's being shown here. If A has a length of 3 meters, then 2A must have a length of 6. Okay? And because the length of a vector when it's drawn represents its magnitude, you actually have to draw it representing that difference in scale. Okay? We can also make vectors shorter, so A over 2 is 1/2 A. So you just make it half as long. But I also showed you that we can do it negative as well. All right. Now we have to learn about something called components. This is a very important part you have to understand in order to, well, really continue with the rest of the course. This is crucial. All right, so imagine you have a ball. Okay, so you see this red ball right here. This red ball is going to travel along this diagonal line. And as it does so, you see these other two circles here, the green circles. The green circles are going to travel along the y and the x axes respectively. And what they're going to represent are the shadows of the red ball along the x and y axis. And that's what's explained in the red box, right? So I'm going to do that a couple times so you can see it. Or you could technically just pause the video and do it again. But notice as the red ball moves, so do its shadows along the x and y axes. Now, since this, the trajectory of the red ball is, I mean, you can see the angle is closer to the x-axis, therefore it has a larger component in the x direction. Okay, so this is its shadow in the y direction, this is its shadow in the x direction. Now, this is what we're trying to do. We're trying to resolve the red vector into its component vectors. Okay, so let's say the red vector, this ball has traveled a distance of 25 meters in whatever direction this is. Okay. Now its shadow in the y direction is 9 meters long, and its shadow in the x direction is 23.3 meters long. And that is simply determined by grabbing a ruler, figuring out the scale, and measuring it along each axis. Okay. Now, if you take the shadow along the y-axis and you translate it to the right, all of a sudden you get a right-angled triangle. So I'm going to show you this here because I think it might be easier for you to see. So we had the 25 meters and it had a y component, which was 9 meters, and it had an x component, which was, actually this should be a little higher, an x component, which was 23.3 meters. And so all they did is they took this arrow and they shifted it over here. So now you have 25 meters and you have your 23.3 meters, and this thing again got shifted towards the right, and I have now 9 meters. Now in this case, hopefully that's not confusing to you. I've actually reversed how the lines are done. I have a solid line now for the resultant, and I have dashed lines now for the components, as long as they are different. Okay, so that's the main thing. Notice that x, so this is in the x direction, and this one here is in the y direction. X and y are perpendicular to each other, just as north and east are perpendicular. So that's a 90-degree angle. So I have these two perpendicular vectors, which when added together give me the resultant of 25 meters, right? Because if I start from the tail of my first vector, which is x, that's right here, and I finish at the tip of my final vector, which is the 9-meter y, I can draw my resultant or my sum from the tail of my first vector to the tip of my final vector. So this is kind of like the sum. But instead of taking the x and y components and figuring out what the sum is, what I'm doing is taking the sum and breaking it into its component pieces. All right, so for instance, if I had a vector like this, let's call this 14 meters long, this one's going up and to the left, I want to break this down into x and y components, right? So pretty much I want to break it down into two perpendicular legs. All right, and so one leg is going to have to go to the left and one leg is going to have to come up. And these two are at 90 degrees. The only difference here is that this time the x component, this is in the negative x direction, and the y component, well, the y component's still in the positive y direction. But I'm breaking up a vector into its component pieces. Notice the x plus the y equals the sum. That's the main idea here. Let's go back to the slides. Okay, so this 25-meter vector is getting broken into 23.3 in the x, 9 meters in the y. There is your 90-degree angle creating your right triangle. And that's the idea. We're breaking vectors down into their components. Now, if a vector is already traveling along the x-axis or the y-axis, so if this red arrow was just along x or y or negative x or negative y, well, then there's just one component to it, right? Then, if, for example, if this red arrow was just along the positive x-axis, there wouldn't be a y component to it. It wouldn't make sense, and you can't create a right-angled triangle from that. But as long as the arrow has some shadow in the x, some shadow in the y, it can be broken down into components. Okay. Now, usually we call the components x and y, like you can see here. We have a sub x and a sub y, and that's usually just the convention that's done. Some books call it a horizontal and a vertical, but it's not always the best choice because y isn't necessarily vertical. although some people use it. Some people use a parallel and a perpendicular. Well, we're not going to get into that. But here we go. Here's vector A. We want to break it up into its components, and there's two ways of doing it. So what you do is you put it into a rectangular box. Okay, now the x component, that's represented by the blue arrow. Here it's called a horizontal. Again, it doesn't matter which one you want to call it. And you can have a y component, which is the vertical component. Okay. Now you can take that vertical component and stick it on the right, and you form your right angled triangle. The vertical and the horizontal components meet at 90 degrees. Hence you have your sum. Now the question is, well, how do you find out these components? I mean, you can't always just use a ruler. That's going to take a lot of time, and it's not exactly correct. So usually what's going to happen is you're going to have the magnitude of the vector A. Okay, maybe this is 6 meters or 10 meters per second. Maybe this is a speed or a velocity. Okay, you're going to have this angle, and using the hypotenuse of the right angle triangle plus the angle, you're going to figure out the other two sides. And if you've already put the pieces together, you're going to need SOHCAHTOA for that. It does say you can measure it with a protractor. I'm never going to ask you guys to measure it with a protractor. You're going to be given the angle, or you'll have some way to find the angle. This piece right here, it's explaining what I was showing you at the very beginning that I promised that we would get back to. The angle is represented by this funky little letter here. It's kind of, it looks like a zero, slanted zero with a line through it. This is the Greek letter theta. Usually when the computer types it, it looks kind of plain like that. But usually when you draw theta, it looks something like this. I always draw mine with a little tick coming out of the end. Some people just like to draw it like this. It's up to you, as long as it doesn't look like an 8 or a 0. It should look distinct. Okay. Now, if you have SOHCAHTOA, which you can use to help you solve the right angle triangle, you can also use Pythagorean Theorem, and that's also what I explained at the beginning. Right? If you have two sides of a right angle triangle, any two sides, you can find the third side. So that's just this. All right. So we've got our angle theta, we've got adjacent, hypotenuse, and opposite. This is just SOHCAHTOA, right? So this is what you would have learned in grade 10 math. Sine theta is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent, right? SOHCAHTOA. So I really hope that's familiar. If you need practice with SOHCAHTOA, you gotta get in touch with me right away, because this is barely the tip of the iceberg in terms of the calculations we're gonna need to do in this course. So make sure you let me know. All right, now for sine theta, we have opposite over hypotenuse. So for our angle theta, opposite would be AV, right, the vertical component, and the adjacent would be the horizontal component. The hypotenuse is just the magnitude of the final vector. So we can stick these letters in here as well. When we do problems, it will make much more sense how to exactly plug all of these values in. You don't necessarily have to memorize all these letters, okay? I'll show you how to do the problems when we get to those. What is sine 25 and cosine 25? Okay, so this part is just grab your calculator, punch in the values, and we're going to get some portion here, some ratio. All right, something to remember is that sine and cosine are always going to be having a magnitude between 0 and 1, right? Magnitude between 0 and 1. Both functions oscillate between y is equal to -1 and y is equal to +1. But the magnitude is always between 0 and 1. And so that means you're always going to have some percentage of your original vector, but less than your original vector, okay? All right, so that is the end of this, this lesson. We've just got this one slide to go. We'll just do this one quickly, but it's just a review of the grade 10 math. A student walks 45 meters on a staircase that rises at a 36-degree angle. Let me just get rid of those. Rises at a 36-degree angle with respect to the horizontal, the x-axis. Find the x and y components of his journey. All right, so let's go to the sheet here. All right, let me just try to fit this here because it is the last piece example. Okay, 45 meters on a staircase. All right, 45 meters, and it's at an angle of 36 degrees with respect to the horizontal. So theta is equal to 36 degrees. We have to find the x and y components. All right. Notice that the picture, well, in the solution, the first line that you actually see on the slide, it says a picture helps. I'm going to be telling you this over and over again. draw a picture for these problems, not just for this problem, but for every problem in physics. It will help you to visualize the problem and help you determine how to solve it. Not to mention it's for marks, right? It's part of showing your work. So it's required and it's helpful. All right, so we're going to take this 45 meters and we're going to break it down. Now the x and y components, what I like to do is always draw my compass directions. So here's x, here's y. Positive x is going to the right, positive y is going up, and I just stick a little plus sign like this. The reason I do that is some questions you actually might want to define your positive directions differently. Maybe you want positive x to be to the left or positive y to be down. Maybe it's a question where the ball is just falling and you don't want to deal with all numbers that are negative. So it's important for you to always draw something like this. We'll continue to do stuff like this in later problems. All right, so I have to break it down into a component that's horizontal and vertical, x and y. So I'm going to break it down. So here's my x component, right? It can't go past the tip. And my y component is perpendicular to it, and it meets it at the tip. I know this angle is 36 degrees. Let's give this vector a name. Since they're walking 45 meters, that's a displacement. So let's call this s. S is 45 meters. So this is going to be s sub x, and this is going to be s sub y. All right, so s sub x, this is adjacent to the angle. And so since it's adjacent and I have the hypotenuse, I'm going to use cosine. All right, so cosine of 36 degrees, cosine is adjacent over hypotenuse, so that's s sub x over 45. So now you have to get s sub x by itself. That means you multiply both sides by 45. S sub x is equal to 45 times cosine of 36 degrees. So grab your calculator, 45 times cosine of 36. Oh, by the way, make sure your calculator's in degrees. I doubt you guys have your calculator in radians, but a common thing once students start studying grade 12 math is that the calculator starts going into radians. That is the true unit of angles in mathematics. And so then when they start taking physics, they have to go back to degrees because physics does not use radians until university level. So anyways, just make sure there's a D on the top there. All right, so 45 times cos 36, and we're going to get, what is that, 36.4 approximately. 1 decimal place is okay. If you want to put more, depending on what kind of problem you're doing, you can. Meters, s sub x, we're only looking for the components, so I just need the magnitude here. But I know the vector is going in the x direction. Now for the y component, s sub y, this vector in this side of the triangle is opposite the 36-degree angle. So I have opposite and I have hypotenuse. That's sine. So sine 36 is equal to opposite, which is s sub y, over hypotenuse, which is 45. Now, some of you might look at that and say, well, I know s sub x as well. I can just do tan. You could. My advice, don't do that unless you absolutely have to, because you had to calculate s sub x. If you made a mistake in this calculation, you're going to carry it forward to this calculation and make more mistakes. Always try your best, if possible. Sometimes it's not possible, but if possible, use information that's original to the question to figure out your unknowns. Sometimes your hands are tied and you can't, but if you can, do that. 45 sine 36. So 45 times sine 36, that's 26.4 meters. Something that I like to do at the end of each question is ask myself, does that make sense? And it does. You see, I've drawn the angle roughly close to 36 degrees. 36 is less than the halfway mark of 45 degrees between vertical and horizontal. And based on my picture, I can see that the y component should be less than the x. And that makes sense. That's what I've gotten here. All right, let's go back to the slides, which are just going to communicate the same things here. Okay. The last thing I just want to show you is that what it means to resolve a vector. The word resolve, if you ever see that, resolve a vector into its components, it means find the x and y pieces. All right. To find the sum or to find the resultant means take the x and y pieces and add them together. To resolve means take the final vector and break it down into its x and y pieces. So the opposite. That is it for today's video. All right. So stay tuned for the next video.